Okay, something unfortunate happened. The recording stopped after 12 seconds. I don't know why. So, pay double attention, then we'll also be maybe okay. Sorry about that, but you know, there is enough space. Alright, the forward algorithm, which is slightly reminiscent of the one I talked to you about, the Viterbi algorithm. So now we don't talk about finding the best path, but summing the probabilities over all paths that a given input sequence has taken, possibly taken through the model. And this is again the slide on how do you calculate pathways. You've seen that before, so I can go on. Now, here we have one example of a path, and I showed you that one. And as we said, one single sequence can be emitted using a large number of potential pathways, possible pathways through the model. As written here. Okay. What's the problem? How do you find an algorithm for this? Because if you want to just, calculate all possible pathways, and you have a big model, this will be even more exponential than the number of possible sequence alignments. And I don't know if you remember, but for a sequence, two sequences of 100 long, the number of sequence alignments, possible sequence alignments, 10 to the power 300. Put that to the power 300, that number, and then you're roughly here, so forget it. Not really impossible to do it like that. So we need a clever algorithm, and dynamic programming is such a clever algorithm, and it can compute all of these possibilities very efficiently. And again, use each of the states and the letters in it, you define that as the probability of being in state K, right? That's what we did before. And we use the same algorithm, so again, it's a recursive algorithm. Okay. So, what's the only thing you need to know? In fact, if you are in this box, you need to think, how can I get into this cell to emit a symbol in the sequence that is here? You could only get in this case, in this model, by coming out of this cell through this transition probability. And of course, the other possibility will be of if you're before in this cell, you will get back into it. And that is, you can get into F4I, any of these letters, by coming from F2 here, if you have sequence symbol I minus 1 there, or in F4 if you had I as this same cell, if you had the preceding sequence symbol in this cell. So that's how it works, as you've seen already. Now, here's the algorithm. And you see the difference was before there was a max sign here, and here now there is a summation sign. So basically again, you see that the probability of something being in cell I is now, you are in that cell, so you emit that symbol in state L here, you emit the ith symbol of the sequence, whatever the letter is, which you multiply it by being in any preceding state called K. And those preceding states are the states, if they're non-silent, of the preceding letter of that sequence, all possible one. This could be thousands of different states. It is more than 3, and times what was their score, times that transition probability from this state K into the state L we're currently in. Yeah? And here you have the same thing for silent, and again you'll see that the emission probability is missing. And the index of the sequence is now not I minus 1, but I, because the sequence stutters in its silent state. I was here, I don't say anything, and then I go on. Yeah. So that's all pretty straightforward. And in the end, as before, how do you get to the end? You add up all of those states that would end up into the end state. Not the best, again, but of course all of them. If you do it like this, you basically, because on the one hand you could say, I walk each of the path, this one, now this one, and now that path, and I add all of those total sums up, that's exactly the same as saying in each state, I look, how could I come in, given the history, and build it up like this. So in the end, you will have effectively the sum of the probabilities pertaining to each of the individual possible pathways, okay? And that is what you are about. So if you carry out this algorithm, you've answered the question, what is the total probability, the total sum of all these possible probabilities? Question?
Yeah, so these silent states, are they like in the example we've been given, there's a begin state and an end state?
Yeah, so this would be an example of a silent state in the middle somewhere. Okay. You carried that you were through 3 non-silent states, and now you go in a silent state, and then out in a non-silent. That's this. So in practice you won't use it. Also in your assignment. And even Durbin says it's so unlikely, I've seen it so few times, you see. He doesn't even talk about it. Okay. But for completeness sake, this is about hidden market models. This is also possible as a tool to do something. Split your sequence, whatever you need, you can do it like this. Okay? Alright, so here we go. This is back to the last one. Fire your question.
So how would that work, a silent state in the middle of the sequence? Because then you stay in the same position, right? So
yes, that's exactly right. That's it. You stay in the same position of the sequence.
Yeah, but then if that position is in a silent state, then how do you ever get beyond?
Oh, if you go from one silent state to another silent state.
Well, I mean, if you're saying like that position is in a silent state, or is that?
No. The position you will be in the silent state is the position of the state preceding that silent state. Basically, right? It stutters.
Yeah.
You were at position 31. Now you go in a silent state, so you do not go to 32. You stay in 31. So what is the position of the silent loop? I would say call it 31 then. It's 31 of the preceding. If you would have another silent state you would go into, but then I would still say I'll call it 31 because that was the last one you had so far, right?
Okay.
And then you go into the next non-silent state, and then relief, you're in 32.
Why would you have an intermediate silent state?
Yeah, okay. Won't happen here. The full tool set, right? This is the hammer, and now we have got the sledgehammer, and for your little, hanging your paint, you don't need the sledgehammer, I hope. I'm just telling you because the toolkit. You see the seconds running? Yeah. I'll wait 15 seconds and I'll stare at the thing.
Maybe try to go into presentation mode in PowerPoint and then go back.
Very good. I like your sense of experimentation. I'll be there. I'll do the real thing. Yeah, maybe you'll find out that I cannot just go from one slide to the other. Now it's just sort of hanging. And hanging here. Oh, it's getting better. Maybe not. Okay. Anyway, let's check the recording. I don't know what's happening, but okay. Let's hope for the best then. But apparently it's not this. Okay. So we have done 2 of 3 problems. We've done, if you tell me what's the best scoring pathway. Now we've done, if you want to know the probability, the total probability of a given input sequence, you do the forward algorithm. And now we go basically to the most complicated thing, and that is training your parameters through a learning algorithm. That's here. We do this via the forward-backward, and that's also called the Baum-Welch algorithm, if you do it iteratively even. Okay, so the learning problem. Oh, it's about setting your parameters. How do you set it? You need, if you're on about, as I said, about a given gene family you want to train your model with, to find a set of sequences that are part of this family, a good representative set, because your model will be as good as your input set is, of course. If you have a lousy set of input with sequences that don't belong to the gene family, you can't expect your model to be very good. Garbage in, garbage out is always what happens in pattern recognition, also here. So get a set of models, but then given a set, the input set, the training set, you should have then a good, well-optimized hidden Markov model given that set that has the parameters reflecting the inner workings of that set, if you like. Yeah. So you would like that model to the best of your intentions. So what is the quantity? So you know, of course, what you wish to optimize is different for different use cases, if you like, yeah, depending on the application. Now, there are two main optimization criteria that are used to abstract parameter values from an input set, and that's maximum likelihood or maximum neutral information. This one is used the most and is related to this, but slightly a bit more easy, so we do this one just, and we've done already quite some maximum likelihood. So let's do that again. So you feel at home a little bit. Okay, so how do we learn? You have a model, and you need a set of training sequences. So now you need to find the most likely parameters to explain, if you like, those training sequences. Your model should harbor the features of the training set. And then, how do you like the goal? If you train it like, oh, the hidden Markov model is going to memorize each and every sequence, that's very clever, of course, memorizing everything. But then if you want to find out, hey, here I find a new sequence, would that belong to this family? You would like to run that new sequence through the model, and then the model should be able to handle it. So that means the model should be general enough that it can handle unseen sequences. If the model would be able to remember each and every sequence in the training set, then it can work on those. And if you put in an unknown set, it says, oh, I've never seen it, I put it 0. That's not good, right? It should be usable. So if you overtrain, overfit, you run into these type of problems. So that's another thing. And in your practical, you'll work on this. Okay, so how could we train parameters if we would know the path? So you know this sequence, for example, it can run like this, and it can run like that, for example, or maybe even one path. This sequence runs like this through the model. Then you can say, that means the first letter goes in here, the second letter goes in there. So you need to set the parameters then that gives a good probability if that is in your training set and sequence. Basically, of course, the way it works is if you want to recognize a certain gene family, your model should, if a new sequence is a member of that family, you would like to see a high score. And if that sequence is not part of the family, you would like to see a low score. So if you know a pathway, you say, okay, then these probabilities should be high for this sequence. Otherwise, you don't trust, right? That's the idea. So if you know the state path, you know exactly where you are, where each symbol of the sequence will run through, will be emitted by, you can just start counting. Over all these sequences, how often are they in this box, in that cell, how often in that box? You count, and you have a good idea of how you should go through this model, right? Basically, can you imagine that we make that the hidden Markov model, you have these boxes and these arrows, and now you think bottom. There is water going to stream through, you put all the water in the begin state, right? And then you squeeze that water through each of those boxes, through these pipes, the transition probabilities, in the end out of the end state. And there should be as much water getting out of the end state as you put in the begin state, otherwise there is something wrong with your model. And now some pathways might be threaded more if you like. Maybe some boxes are walked through more by your sequence set than the others. So that is a wider stream, so more water goes through there. And how do you optimize this? To set these probability higher values. So the float gates. So this helped me, I don't know if this helps you, but I apologize, I will never tell the story again, but the water ID is, so what we threaded a lot should be deeper. Yeah? Have you ever heard about ant colony optimization? It's a great thing. Ants do this. There is an ant nest, say, and there is honey pot somewhere there. These ants, they walk in all directions, right? And then one gets the honey pot, and he eats it, and he's very happy, and he brings some honey back. He's so happy that there's a pheromone, these are external hormones. He sprays that pheromone over the path, and all the other ants, they would randomly walk, but then they sniff, that's nice. So they walk over this sniff pathway, and then they go to they find the honey by that. That's great, so they're also happy, right? Oh, very happy. So this path will be, full of pheromones. All the ants go there, and far more than you would normally expect. But what happens? What's the big problem now? Not within the market, but ants. What if the honey source gets depleted? So this first ant that goes there over this very happy path runs, honey, nothing. Shit. He goes back. No pheromone anymore, right? Goes back, And that means if this happens a lot, then this pathway will not sort of fill in anymore, so the pheromone goes away, so that path fades. And maybe there's another source that was built up. Yeah? So you see this dynamically, you know, and this is what you want to do. So the pheromone is your parameter in the hidden microphone. You know, if that path is good, it's walked a lot, you would like to optimize it by hiring your probability. Yeah? Okay, don't think of water, think about ants. Or think about ants and water. But don't combine it because your ants drown. Right? That's not nice. Stuff your ants through a totally wet hidden microphone. Don't do these kind of things. Alright, anyway. Basically here, if you know the path, things you can count. Yeah? So, you just estimate the count. How would you count? There we go. Here's counting. So is the number, you knew that in this box, in this transition, the letter L was, so many times you went through, given your input set, your finite input set of sequences. So that means for each box, shall I quickly draw that for you? Here is a box again, right? And maybe there are arrows in and all kinds of arrows out. What do I know? Very many, maybe. So, like this. And what do? If you talk about one box, say this box, this is maximum likelihood in a sense, because what do? What's the probability? I have 4 observed counts, and 10 here, and 11 here, and 15 here. If you can read what I'm doing. How do you calculate the likelihood of this box? With 4 observations. Maximum likelihood 4 divided by 4 plus 10 plus 11 plus 15, right? Divided by the total. So you divide, you convert it to fractions of the total possible, right? That's the left-hand guy there. And how would you do the same thing for your, because we need to not only set the emission probability, but also the transition probabilities. How would you do that? What's the situation? Something like this, we're talking about this transition. And how do you do it? There can also be transition like this out of this box, and like this, and another one here. Sorry, you see it? How do you calculate this transition? The probability of this one. You say coming out of here, yeah, this is, I will convert this to the fraction of all probabilities going out of this box. Okay, that's how you do it. And therefore. So this is how you convert observed counts to make them probabilities. Using maximum likelihood, because this is basically doing maximum likelihood. You have a question?
How do you determine the number of boxes?
The number of boxes. That's a very good point. It's a much better point even than you think you make. Because I didn't talk about this. So far we say the model is there, and then you have these emission and transition probabilities, and then you train it. But your question is more fundamental, I think, if you mean that. How do you make a model? What boxes? Okay, begin and end state is there, but how many states should I build? What memory? Hey, this is hard in a sense. This requires knowledge. This requires knowledge about your problem, how to cast it in a model, right? There's no automatic program that will do this for you. I'll have it at the very end if I get to it. I need to rush a bit to an alignment case where that is exactly coming up. Yeah.
The emission of the sound,
Yeah.
from the other state or from the same state? Because
the emission is in the same state. That's this drawing in the same box.
It's not the total emission on one
Observations. State. These are observations. It's if you convert this, then it will sum up to 1. The example 4, 11, 10.
So I count.
You count. You add them up. So I have 10 in each box. What kind of probability would you like to attach to that using maximum likelihood? A quarter each. 10 divided by 40 for each quarter. Does it add up to 1? Yes, so 4 boxes it is. And here you do this, well, the thing, you say, what is the fraction of the observed number of times the transition is taken, normalized by the total number of transitions getting out of state K. This means out of state K. From state K to any other state L. Yeah?
So I don't count how many times.
Yeah, you count. So how many times do I walk this arrow? And how do I normalize that? Oops, other thing. By all the other counts getting out of that box. Getting out of the box. Okay. Another question, yeah.
Yeah, sorry, could you maybe just shortly repeat the middle bit, because I couldn't really follow it.
This
through
one?
Well, no, like the middle bit on the board, because you couldn't really see it very
Ah,
well on
sorry.
the slides.
Then I do it on the, then I do it there, yeah? I write this one, you know this full metal. And I make, oops. So it's just interpreting what does that formula mean, okay? Now we need to find this. You know what? Even more surface from your. How's that? Okay, here we go again. Yeah. So the idea is you knew all the pathways, all these sequences have run through the model, and you find out that you went 5 times through here. Okay? So how do you normalize this? We need to go to a fraction, to a probability. So that's by maximum likelihood, then you decide. So how it's done, you say, okay, maybe this one, this cell also can go to this state, and to another state. And these have counts, this was maybe 3, this was maybe 15, you know. And you say, how do I normalize this now? You say, if I want to know this one, convert it to a probability, I relate it to, in what other ways can you get out of box, what was it? K, this is state K, this is state L. You say getting out of K. And in this case, if these were all the counts observed, it would be 5 over 5 plus 3 plus 15. And this one would become 3 over 5 plus 3 plus 15. And that guy would become 15 out of 4. And so on. Yeah? That's just that. So you going out of the first state, yeah? For a transition. That's this, okay? And this is called maximum likelihood. And you can easily count, because you knew the state path. You knew how all these sequences were being emitted by the model. Okay, now after a few. So, okay, if you see that there are 0 observations, you know all of this stuff, right? I will go on. This is sort of known to you. Pseudocount. Now we go into the real thing, because I need to do this, otherwise I cannot possibly send you out of this room. Okay, there we go. Now we have a bit of another problem. This was if you know the state, if you know the path. What is your problem if you have a sequence? You have your forward algorithm, you know at the end, going over all possible pathways, maybe 1 million or so, add them up, that's your score. You have no idea of what pathways are being taken. You don't know an exact path, it's a mixture of very, very many. So how can you still use this thinking and set your parameters, having that idea of the water model, or your ant model, whatever you want to use methods. Yeah? Basically what you say is you use the expected number of times you go through it. You cannot really count, because you don't know the pathways, but you can work in a probabilistic framework. If I can sort of find an idea of what would I expect to go here, I can convert that sort of to counts, and then I can do the same thing, and then I'm there. And that's basically what we will do. We will look into this expectation, and if we have these expected counts, now it's just an expectation, it's not a counted number like the moment ago. You can maximize this in the very same way, and then you know how to do. So how would this work? I'll give you an example. We have, what's the sequence? We have an input sequence, C-A-G-T, okay, 4 letters. And now we're on about what is the probability if I have the letter G here. What is the chance, given the sequence, that the letter G would end up in this box? So not the letter G in that letter G should not be in that box or that box or that, in this box, in that state. How can you do this? Well, let's first, so what can we do? Now, we have to put this in 2 things. The idea is now, how can I find out whether that letter here ends up in this box? Well, if I would look in, what does it mean if G ends up in this box? That the sequence, starting in the begin state, should, by going through the letter CA, then end up here. So you use this. Where should CA go to end up in the 3rd letter here? How many possibilities in this case? Not so many, right? 1. Ah. 1. Sorry. I think 1. 1 possibility. You can start here. What do you do? First letter here. Ah, sorry, you're right. 2 possibilities. Clever than I am. Very good. Nice. Yes. So here, we go back here, in here, or go here, go there, and back in. Yes. Very good. Okay, you corrected me. Great. Okay, so that's getting there. Now we know how to get, and what should we also know to get a good estimate of the box? We should also finish this letter nicely, this sequence nicely. So here we go. You answered this already, right? This is one way to go there, and you're even better than this example seems to say only this one, but yes, there is the possibility of doing A and C here and then back to G here. The model tells you can do this. So this is for getting from the beginning into G. Now we need not to cheat, we need also to finish the job. How do you do that? So what's the next step? Will it work? Here. How can we get out of the letter G in this box? How many ways? Oh, I'm right, guys. It's not one way, only one time, right? Because if you have the G here, you need to go to the end state. You can only do this by getting the T expressed or emitted also in this box. So you have to go back and then out. So what is it? The combination. If you want to talk about the likelihood of this letter G in this box, you talk about the first bit. And what was a nice algorithm to get to the total probability of ending up in a state having a sequence or a subsequence? The forward algorithm. And now you may guess what would be the kind of algorithm to say how do I do the letters following that symbol I'm talking about. It will be also the forward to the end, but it's called that. That's the idea. Yeah? Happy enough? Then we go. So guys, here we go. This you saw the forward algorithm a while ago. It has the same ingredients. You know, Durbin is sometimes doing annoying things. One of the annoying things is that the end state, what number would you like to give the end state? If the begin state is 0, your sequence is 100 long, tell me, what would you do? Call the end state 101? Yeah, what does Durbin do? I call it 0 as well. Okay. So how do you know the end state is at the end, right? The begin state, but they're named the same in Durbin, right? So he also talks about, so I'm following Durbin because that's your course book. You can do all of these things in very different ways, but this is the way Durbin does the bookkeeping. He says this is going from any state K to the end state, which is called 0. The letter E would have been a bit more descriptive of this. But okay. Next book by whom? Not that many. So, why is this the back? Because what you see, you go from the end state, you walk back from the end state to the box we're talking about. Yeah. So it's the same thing. This is if there is an emitted state. So what do? Going backwards in the sequence from the end state back to the earlier state, you have this transition probabilities, of course, the emission probabilities, and so this is the index. So you go to sequence I, you come in the reverse direction, backwards. So the preceding letter now, if you go backwards, was of course I plus 1. If you are in I, you go in against the sequence, your early one is I plus 1. Yeah. So why is this now? This is the silent state, and again, just like before. The letter before is the same letter because it's stopped. There is no emission. Yeah? Same thing as it before. Okay? Now, there's one little bit annoying thing. I have to tell you, and there's a good reason why Durbin does it, but the bookkeeping goes in. Normally, in the forward algorithm, this would have been the transition probability, the emission probability of letter I would already be in. Here. Okay. Go back to the forward. Sorry, move it like this. Where is the forward algorithm a while ago, right? Sorry about this, but if you want to know, show you. Was it here? Yeah. Here, you see the index of the emission probability. This is about cell. The letter I in state L, it's the I symbol here. Now we go forward. I plus 1. One further. It's out of sync a bit, but it doesn't matter. It's a different way. Why does he do this? There's a good reason for this. Here is what I just told you. Forward scores includes. Here does not include emission probability of I, only of I plus 1. And this, to put it mildly, the slight asymmetry is made to make things look better. There we go. What do we need? So, again to this picture. Let's do the first picture. Here, this one. So, if you want to know the probability of this letter, estimate the count, the probability of this letter in this box, this letter in this state, letter G. We talk about the forward algorithm until G from CA, and the backward algorithm from T. So all of this sequence, given that the letter, you pin down the letter, I enforce like this, that this G is here and not anywhere else. That's what we talk about. So, what is in the end the probability of the of this total sequence? Well, the probability of the forward algorithm till that moment times the probability of that backward algorithm. That will be the total probability of that sequence, given that it runs through it. Okay? Now, there we go. Here is the slight asymmetry. And now, this is exactly what you see in Durbin, the forward algorithm. So we talk about the letter I, state K. So the forward algorithm going from the beginning to state K, and the backward algorithm getting from the end to the sequence, the end state if you like, back into state K. Yeah? So you can do this because of this asymmetry. This you can write down like this. No further housekeeping. Now, what is this? What do you say? A. In how many more ways can you put this letter? Well, you can do the same thing for that same letter in another box, right? Make the count. So you normalize this using the total probability for that sequence. How did you calculate the total probability? What algorithm is that? The forward algorithm, right? If you arrive in the end state of the model, you have had all possible pathways and you add them up. What would the backward, can you use the backward algorithm for total probability? What do you think? How does the backward algorithm run? It starts in the end state, does the very same thing. Where does it end then? In the begin state. So where is the likelihood, the total probability? In this case, in the begin state, if you arrive there, if you walk against. Right, so that's. All right. So here now we go to what have we got here? These are the calculations. These are probabilities, right? These are emission products of emission and transition probabilities. Now we're going to make them. This is the. So far we've calculated for a single sequence. How many sequences do you have your input set? 100. So do we have to know? This probability in this box of this letter in this sequence, but also a letter B in another sequence. So you need to add up all those probabilities given all your sequences, and the index for all your sequences is J. So maybe there are 100 sequences. You would sum all these probabilities from 1 to 100. Given in this case that in this special box, this letter B is there. Yeah? The forward times the backward. You sum over all input sequences to get an estimate of how much water, if you like, is in this little box for this letter in this state. Okay? And this looks a bit more complicated, because this is the same thing for this a moment ago it was for the emission probabilities, this is for the transition probabilities. Now, what have you got here? This is, you do the same thing, but this is for all sequences that run through in between a given box I and a given box J, or a given box K and a given box L. Yeah? Here, from K to L. How, here. So what do? We talk about this box, yeah, and we talk about the transition probability following that box. So we had the emission probability in this box, and now we need to talk, so how do we get in this box? By the forward algorithm. And how do we get back into this box? By the backward algorithm into this box. And what do we not have now? So, the forward algorithm till that box I. The backward algorithm you run until box I plus 1. The letter, but in this, in this box. So what do you need to connect it to? The KL, the transition probability, plus this emission probability. Why? Because Durbin in the backward algorithm didn't put that one in. That's the asymmetry I pointed to you a moment ago. So this is how you need to solve it. So it looks nice in the sense of this asymmetry, and here you see back that for your housekeeping you should not forget this emission probability.
So is this state on the first?
This is the one, in fact, for this state. Okay? Look at it during your practical. If you start programming, you'll see how it works. Okay, now, what have you got now? We have sort of counts, probabilistic counts, given the model, given the water you divide, right? And now given, you know, these are numbers, and it doesn't, so now you convert it to probabilities using the very same thing you explained before. Only the counts from this algorithm, okay? Okay, so, what have we got? Now we do the real bioinformatics, then think about your model or what, it doesn't matter. What do you need to do to execute a model? How can you execute? How do you train a model? We need these probabilities already, right? What do you need to do? You need to start somewhere. What do you? We guess the parameters first. Hopefully we guess them pretty good. If you have a complicated model, you might be totally wrong. So you go to databases or anything, or you just guess. I put all the values evenly because I have no idea. Okay, it's called your prior. Then you do this. You have your input set of sequences. You run them through. In the end, you get your parameters, right? Given those bad priors. But your set of input sequences. Now you have posterior probabilities, given that you trained using input sequence. What can you now do? Use your posterior set of sequences. Do the whole thing again. You have now an informed prior, better prior, and now you run the whole thing again. Train using the same input set, but the new set of parameters. And if you do this a couple of times, you find that you optimize your value. These algorithms are called hill climbing algorithms and optimization algorithms. You take a step that you have a landscape, you take a step up. If you're all the time in a landscape, take a step up. You're here, and here I go down, I don't do this, I take a step, here it goes up, I'm higher, so now I'm a bit higher, see this? I stand a bit higher, and now I take another step. Where will I end up if I do it? Okay, at the top of the mountain. Will this be the highest mountain in the whole landscape? If you do this? The answer is no, because you're on top of this mountain. You can't go up anymore, but the only thing you can do is step up. Hey, shit, I'm on the wrong mountain. This one is higher. You see it there on the top, right? So, what does that mean? In fact, that your prior, what if you would have been at the foot of this highest mountain? You would have gone up that one. So basically, start with a number of different priors. And this is the idea with this optimization. Do you get it? So, basically what I'm saying, that you find out I'm on the wrong mountain, is called, you ended up in a local maximum. You want the global maximum, the highest mountain. And you do this by starting at many different points in the landscape, because then you have the chance that you walk the highest mountain. Okay? So this is how you do it. What is nice about this procedure is that what does a good set do? I already told you. You have trained your parameters, and you train them again. You have your set of input sets. What do you want? You want to recognize that input set. What would you like your total probability to do if you train? Should it go up or down? Should it go up? So you can score this by score all of these likelihoods, take the log, that's how they do it. And that is a single number that tells you how recognized is my input set by the model. And of course, if you train it, you hope that it gets all the time better. Yeah? And when do you know you train on and on? When does it help anymore? Well, if your parameters go down, God forbid. Or what might well happen is, it gets stable. And then you can stop right and use it. Okay. So, viterbi training. I don't know if you can take that one. Oh, I should control to range. You know what? This is part of the practical. Viterbi training, what was that again? You know the path. So that is the training that I taught you initially, right? Okay. You do this during the practical, the guys will make this clear. So many questions. You know what I will do? Other techniques to do this. That's fine. I show you a few slides, but I would like to end up with the work of art. That was your question. Here, I give you an example. Okay, this is for multiple alignment. There are Markov models possible for multiple alignment. They talk about match states. When letters are put in the model, when a new sequence is added to the model. Okay, this letter aligns with this column in the profile, if you like. And then there are delete states. No, the letter will be opposite the gap, so it won't be put in the model. And you have insertion states, So gaps in the profile or gaps in the sequence if you align a new sequence to it. Now, this is, here you see, these gray cells are put as states, as match states in the model. And here you see it's a work of art, why not these? And then there is a simple rule. Here you say, okay, this bit of the alignment is just varies too much. There's not enough conservation. Oh, leave those out. But there is no formal rule to say you should do it like this, right? And that's the art bit. So building, if you like, the topology of your network, of your Markov model, is the understanding of the problem and how to, you know, will you go using a knife or a hammer, you know, how you build your model, that is in the hand of the user. Okay? Once you have decided, this will be, then you can start training the parameters of each of those boxes. But how you get to this setup in the first place is basically a work of art, in a sense. Yeah? Let's put it differently, understanding the problem, what kind of model would be best for your given problem. Yeah? And there are no fixed rules. Okay. Yeah, I should stop because, you know, by 3:30 the guys will have to run away. So, I think this is, yeah. So the three problems, that is, you should understand, right? Viterbi, best path, total probability, forward, and for training, you need forward and backward, combine them, and you carry them out into the
Backwards if you not use them.
No, not because normally the forward and backward is just, you know, you think a bit. You could also say the backward element is for total probability, it works the same.
And then we find the same.
Yeah, yeah, it's the same thing. In the other way. Yeah? Maybe it's a lot of housekeeping, you know, it might seem complicated, but don't worry about it. You know, if you go into your assignment, I guess it will be clear soon. This worked over the years so far. Now I'm ready.